one thing I want you to do first is I want you to extend this a little bit longer. Extend this graph a little bit longer. Go beyond than the point A, like anywhere. Just go beyond than A, like that. The shape is not good. Okay, let's call this point D. And then give here an endpoint, call this point E. Okay, there are 5 points, okay, A, B, C, D, E. So let's talk about the name of each individual point on this graph, okay? The name of each individual points. So first of all, A, B, and C, those 3 points are called stationary points. They're all called stationary points. Okay, so A, B, C are stationary points. And D and E are called endpoints. D and E are called endpoints. So what is stationary points? What is stationary points? The stationary points is the points with a horizontal tangent. Okay, at that point you have a horizontal tangent. So can you have a look? A, B, and C, I have drawn the tangent out. They all have a horizontal tangent. So they are called stationary points. But we can classify that into small subgroups as well. A is called a maximum turning point. Well, let's put a word local. Local maximum turning point. Well, I can say it's a local maximum, or I can say a local maximum turning point. Well, they're the same thing. So it's a turning point and it's a maximum turning point. I can call that a local maximum turning point. Therefore, C is called a local minimum turning point. Okay. B is called a stationary point of inflection. Stationary point of inflection. Okay. These are the names for those 3 points. Let's have a look at D. Okay, from E to D. D is the highest point of the curve. Okay, D is the highest point of the whole graph. So we call that a absolute maximum. Okay, we call that absolute maximum because that's the absolutely highest point. Okay, A is called the local maximum because A is the turning point. That's just the name of it. Okay, local maximum. Like about that area, that is the maximum. But look at the whole graph. D is the highest point. So D is called the absolute maximum. Okay, D is called the absolute maximum. Then we will have absolute minimum. We will have absolute minimum. So what is the absolute minimum? That's still the point C because C is the lowest value. So this is also called the absolute minimum. It can be the absolute minimum, also it can be the local minimum. Okay, it can be, this point can have like both names, okay, both names. So local minimum, yes, because that's a turning point, minimum turning point. And it also can be the absolute minimum because that's the lowest point for the given domain. Okay, for the given domain, that is the lowest point. Okay, that's just some names we'll learn for this exercise. Okay, we learn types of stationary points. Okay, how many types of stationary points we have? We have 3 types: local maximum, local minimum, and stationary point of inflection. Well, this stationary point of inflection is a decreasing one, but we also can have an increasing stationary points of inflection like that. That is a stationary point of inflection as well. Okay, that's a stationary point of inflection as well. That's an increasing stationary point of inflection. Okay, increasing stationary point of inflection. Okay, so let's have a look. Why we talk about like stationary points? Because they are the special points if we look at the derivative. All of the points with like A, B, C, they all have a horizontal tangent line. And the gradient of the tangent is called f dash x, or say dy dx, is the derivative function. They got a derivative 0 because the gradient of the tangent for A, B, and C are 0. Okay, the gradient of tangents at point A, B, and C are 0. So the derivative for stationary points are 0. Okay, the derivatives for stationary points are 0. So the derivative of a function gives its gradient function. That is, gives the gradient of the tangent of the curve for any specified value of the independent variable. So basically you need to remember the derivative is the gradient function of the tangent. Okay, derivative is the gradient function of the tangent. So basically the sentence want to talk about that. Just go to ask any teacher to give you. They can write more for you. Okay, so the derivative of the gradient of the tangent. Okay, so when the derivatives equals to 0, the tangent is horizontal. The tangent is horizontal, and then they are called the stationary points. Okay, we have a derivative equals to 0, then the tangent will be horizontal. And then this is called the stationary points. Okay, that's the stationary points. So in other words, a function f(x) has stationary points when f dash x equals to 0. Okay, when f dash x equals to 0, you have the stationary points. So that's the most important thing. If you are asked to find stationary points, you need to find f dash x equals to 0 and solve for x. Okay, solve for x. The x gives to you are the points with stationary points. Okay, are the points with stationary points. Stationary points always occur when the gradient equals to 0. Okay, when the gradient equals to 0. So there are two main types of the stationary points. Okay, we have the stationary point of inflection, which is called the spoil, and we also have turning points, which is called the local maximum and the local minimum. Okay, we have like for the stationary point of inflection, we can have like increasing stationary point of inflection. We can have decreasing stationary point of inflection. For the local maximum, we will have this type of turning points. Local minimum, we have that point. Okay, that's the stationary points. They are called the stationary points because the gradient of those points are 0. Okay, have a think about this. When you have f(x), you derive it, got f dash x. You solve that equals to 0. You got like x equals to a, x equals to b, or x equals to c, like 3 values. Do you know which one is maximum, which one is minimum, or do you know which one is stationary point of inflection? Can you distinguish between the points? Well, you solve out the stationary points, like f dash x equals to 0. Okay, we solve it. F dash x equals to 0. And we solve out, for example, x equals to 1, x equals to 2, and x equals to negative half. Can you tell which one is a turning point, which one is a stationary point? Can you tell that? No. Okay, you just solve out some points, give you a gradient equals to 0. But you don't know what those points looks like. Okay, it can be any of those four graphs. Can be any of those four graphs. So you can't decide whether it's a stationary point of inflection, or whether it's a turning point, or it's a maximum or a minimum. The only thing you can tell from f dash x equals to 0 is those points are stationary points with tangent, horizontal tangent. That's the only thing you can tell. Okay, so there are 3 types satisfy what we're trying to solve. It's like a stationary point of inflection, a turning point, maximum, or minimum turning point. So what we need to do after we solve out those values is using a table to test it. So this is called the slope diagram, the table, or we call the table method. We need to use that to test what our graph looks like. What our graph looks like. So, well, I'll tell you like in more detail later for next exercise. But like, let's just look at it. That's 4 types, okay? local minimum, local maximum, stationary point of inflection of a positive shape, and local a stationary point of inflection of a negative shape. So that's the four type. That's what the slope field I should see for each of this type. Well, I can see what our slope diagram should look like if it's a maximum. That's the first one. So at the point A, I should have a horizontal tangent. That's a tangent 0. And on anything on the left of A, I should have an increasing diagram, okay, increasing gradient. And on the greater side, I should have a negative gradient, which is a decreasing. Then I can have a local maximum. Okay, I can have a local maximum. I'll talk about that further in the next example. Okay, let's just have a look at this example. Find the stationary points and state the nature of the points of the following function. Okay, I want to find stationary points. I want to find stationary points. What I need to do first is find dy dx. Because stationary points is gradient equals to 0. Okay, stationary points is gradient equals to 0. So dy dx is, no, I know this. Okay, just come back to class then. 12 and minus 4x. Okay, 12 minus 4x. Okay, dy dx equals to 12 minus 4x. So I will solve dy dx equals to 0 to find which x give you gradient equals to 0. So I'll say 12 minus 4x equals to 0. I want to find that is the gradient of tangent equals to 0. Okay, it's the gradient of the tangent equals to 0. What I'm trying to do here is make the gradient of the tangent equals to 0. Then there must be a stationary point. I can have x equals to 3. Okay, you solve out x equals to 3, but you don't know whether it's a maximum, a minimum, or stationary point of inflection. So what we need to do is like a very important thing. Okay, this is very important. Please listen carefully. Like in year 12, you need to test it. Okay, you always need to test the nature of a stationary point because you don't know what point is that. Like you don't know whether it's maximum, minimum, or stationary. Like you always need to justify your answer. Say, okay, this 3 is a maximum or this 3 is a minimum. So how do we do that is using the table method. So we will draw a table. Okay, the table is always 3 rows. Okay, how many columns is depends on how many stationary points we have. Okay, we have just one stationary point. So what I will do is, I'll tell you what to do. I will have x in the first place. Okay, x, that's the x value I'll take. For the second one is the derivative value. So the derivative value, in this case, we have dy dx. We don't have f dash x. We can't write f dash x in this box. We have is dy dx. Or if you have a function v in terms of t, you will say dv dt. You need to make sure the notation in this box is correct. So what we will have is the derivative, which is dy dx. I want to know the derivative value for individual x. That's always the derivative function. Well, derivative notation. Well, whether it's f dash x, dy dx, dv dx, dv dt, it depends on what you have originally. And the last one is called graph. Okay, slope graph. But you can just say graph. And the next column is always empty. The next one, well, I will make it empty first. And the next one, you will put the smallest stationary points in. What's the smallest? Well, we only have 1, so we will put 3 in. And then the next one will be empty. So what's the purpose of that is you have a point, and then you leave 2 empty boxes to the left and right hand side of that point. If you have more, for example, you have a 5. So the 5 will right here. Okay, if you have a 5, I don't have 5. If you have a 5 as stationary, you write it here. And then you will leave another column for 5, and then we stop it. Okay, we stop it. But like we don't have this 5, we don't need that. We don't need that. So we only have like 3 columns, 4 columns is enough, including the name. So what I'll do next is I will select a point on the left-hand side of 3. On the left-hand side of 3. So I'll select a point. So I'll select an easy one because I need to substitute a point in. So what I'll select is I'll select a 0. Well, you can select anything like 1 or 2 or -10, whatever you want. But I'll say 0 is an easy calculation value, so I'll select a 0. And then I will select maybe 3, 4, I'll select a 5 or 4, it doesn't matter, like anything greater than that, I'll select anything. Well, if you want, you can select 3.1, but why make your life so hard, like to calculate? So just select something easy to calculate. So what I need to substitute those points in is into the derivative function, because the next line is the derivative value. Okay, it's the derivative value. So what are the derivative value? You know that the derivative value as 3 is a 0. That's what we solve. At 3, you have a derivative equals to 0. So I want to see at 0 what the derivative value looks like. So I put 0 into this function. You have 12. Yeah. So you write 12 here. And for 5, you put 5 into the derivative function. Okay, always remember, it's the derivative function. You want to look at the derivative shape. Okay, you want to look at whether the graph is an increasing function or decreasing. So you look at derivative value, not the original value. I have a lot of students always trying to substitute into the original function. That's not correct. I want to know the derivative value. So I put 5 into the derivative function. I have 12 minus 20. I have minus 8. Okay, make a note here. The second row must have values. I'm not sure if you learned that or not in like outside like tuition center or something, like you learned that before I start this topic. But according to VCAR report, the second row must have values. Some teachers may just have like, oh, you can write just positive or negative. What all I want to see is that whether it's a gradient, positive gradient or negative gradient. Okay, that's all basically what I want to see. I want to see whether it's positive or negative. There are some teachers, I know some teachers teaching is like, you just need to put plus or minus sign into that. Well, you can have a look. Okay, put 0 in. Yeah, that's a positive value. You don't need to write 12. You write a positive. That's incorrect. According to VCAR report, those row, second row, you must put values in. You really need to do the substitution. Find the derivative value and write that down in that box. You can't just write plus or minus. You must write a value in that. Okay? What is it? It's a value. You can't write plus or minus. So I will have 12 and negative 8. That's why I ask you, try to find something easy to calculate. You just not look at it. You need to really calculate that and put the derivative in. So, well, personally, I think it's not necessary to see what value is actually it is. I just need to see it's positive or negative. It's not really necessary to write the value in. But like VCAR people, why they want you to write the value in is because they want to make sure you know where to substitute. And they want you to know that you are not just thinking, okay, this should be a maximum, so that must be a positive, that must be a negative. You can predict actually according to what you want. So they don't want that happen. So they want to make sure you actually substitute into the correct place and you know what to do with this function. So I think that's why they must, like, you must have the value in that second row. So, but like, I haven't emphasized that to my year 11 student last year, but like this year I want to make it really clear, like this needs to be a value into the second row. Okay, into the second row. And the third row is according to your second row. Okay, you have a derivative. Well, can you think about that? To the point, left point, like the 3 is here, on the left of 3, you always have positive gradient. I select a random point, which is 3. 0. I can select any more. I can select 1. It also needs to be positive. You can't really change positive to negative. So on the left hand side, all the gradient needs to be positive. So I should have a graph. Well, I have positive gradient. I must have positive graph increasing. So this part of the graph should look like that. It's increasing. Well, you don't need to see it's a curve increasing or a straight line increasing. You just need to know that's an increasing function. Because on your left-hand side must be an increasing function. You choose one point, and then you put that into the derivative function. You have a positive derivative, which means that must be a positive gradient, and it's an increasing graph. Okay, let's follow the logic. And then at right-hand side, it must be like a decreasing function because you have negative gradient. And therefore, the 0 is a horizontal line. Okay, 0 is a horizontal line. That's the point 0. And can you see the shape of the graph? The shape of the graph is like this. Well, it can be actually like that, or it can be maybe like that. But it is like a maximum point. It doesn't matter what the graph looks like. It's not really necessary to look at those two shapes. It's not really correct. But doesn't matter how it increased. It always needs to be a maximum point for this turning point here, the stationary points here. So I have x equals to 3. I haven't calculated y equals to what. When x equals to 3, y equals to 9 plus 36 minus 9 minus 18. That's y equals to 9 plus 18, and y equals to 27. So the point 3 and 27 is like I would say that's a local maximum turning point. Okay. Well, I don't know whether it's an absolute maximum or not, but what I can all say is that's a local maximum. It's not necessary to be absolute maximum, but it's definitely a local maximum. So I'll see that's a local maximum point. All right, what I'll do is I'll give you some time to try this question. Can you just cross out the restrictions? I don't want this restriction. I want you to find more values. It doesn't matter t is greater than 0, less than 0. So t can be anything. Just make t belongs to R. And I want you to find the derivative, solve out the stationary points, find out the table, substitute correct values in, and then decide what shape of the graph looks like and what stationary points you have. Okay. Find derivative equals to 0. Okay, so first of all, you have p and t. So this derivative should call dp dt. That's the first place you may do something wrong. You say dy dt, or you can say f dash x. That's all incorrect. So it must be dp dt. That's 6t squared minus 10t minus 4 plus 0. So don't worry about 0. And then we need to solve that function equals to 0 because I'm looking for derivative values. I can divide the 2 on each side. I can divide the 2 on each side because I can make the number smaller and make me more happy. And then I can do 1, 3, 2, 1, negative 2 here. That's a negative 6 plus 1. That's a negative 5. So what I have is t minus 2 and 3t plus 1. That's 0. So t should be 2, or t should be negative a third. Okay, as I said, you should write these things in order. So negative 3 is the smaller one. I should write negative 3 first. But it doesn't matter, I still have 3 rows. Okay, the first one is called t then. It's not x, it's called t. The second one must be dp dt. If you write dy dx or f dash x, you lose 1 mark, half mark maybe. Then the next one is graph. the x1's graph. First one always empty. And then you write the second, like the next smaller number, which is negative a third. And then you put next one empty. And you put next number in, which is 2. And it needs to leave the right hand side empty. Okay, so you set up a table like that first. Negative third and 2. Okay, remember I see someone trying to calculate the derivative for negative a third and 2. You don't need to calculate them. That's just 0 and 0. That's what you solve out from the above line. Okay, the derivative for negative a third and 2 are 0 because you just solved that. And then I will select number. Those numbers are not randomly selected. I need to select, okay, a number on the left hand side of negative a third. I need to select number in between negative a third and 2. And I will select number on the right hand side of 2. So I will select a negative 1 here. I will select 0 here. And I will do, let me have a think. Let's do 3 here. Okay. So for negative 1, I need to put negative 1 into the derivative function. Where's the derivative function? Is that one. Okay, into the derivative function. So when it is negative 1, it's 6 plus 10 minus 4. So that's a 12. The derivative is a 12. And 0. 0 is easy. I have a derivative of negative 4. And the 3, 54 minus 30 minus 4. That's a 20 then. Correct? Okay, so let's have a look at the shape of the graph. 12 is a positive gradient. I should have positive. 0 is a horizontal. Minus 4 is minimum. Okay, it's decreasing. Okay, 20 is a positive, it's increasing. 0 is like that. So the shape of the graph is this. This point is negative a third, whatever it is that. Then that point must be 2 comma something. I need to calculate that out. I need to calculate the y value. That's 20? That's 20? Yeah. Because I put 3 into the derivative and I calculate that's a 20. So it's positive. So negative a third is here, 2 is here. So at 2 is a local minimum and at negative a third is a local maximum. Okay, so I need to work out the y values. So I'll say when t equals to negative a third, p equals 2. Okay, very tough value. 2 times negative 127 minus 5 times 19 plus 4 over 3 and plus 13. Okay, that's a negative 2 on 27 minus 27, 15 over 27 plus 27 times a 9 plus 27, well, 13 times 27 351. Okay, so it's a plus a 36. And minus 17. That's a 370 over 27. Plus that minus a 17, 370. Okay, 370, is that correct? 370 over 27? Yeah, okay, good. My calculation skill is good. Okay, I have 370 over 27 as the y value, that's the coordinates. And I will say when t equals to 2, because 2 is another stationary point. When that is 2, that p equals to 16 minus 20 minus 8 plus 13. Okay, p equals to minus 4 minus 8 plus 13. P equals to minus 12 plus 13, that's 1. So that's 2 and 1. That's the local minimum. So negative a third 370 over 27, that's the local maximum. And 2, 1 is the local minimum. Okay, that's what we do. Okay, that's how we find turning points. Remember when we sketch polynomials, and I said it's different from quadratic. You cannot find the turning point in the middle of the two x-intercept. It's not symmetrical anymore. So I tell you, you don't know how to find the turning point. Like we will learn that later. So that's where we start to find the turning point of the derivative, like the polynomials. So we find the derivative, we make it equals to 0, and we use the table to test which point is which point, and then we put the values in. Okay, that's how we find the turning point of the polynomial graph. Okay, so I'm not going to continue today, but I want you to have a try of example 2 and example 3 before Thursday. Okay, example 2 and example 3 before Thursday. Okay, we'll continue.